This is our next lecture on relative atomic mass. The relative atomic mass is the average mass of all the naturally occurring isotopes of an element. Each one of those mass of isotopes is weighted in how abundant each isotope is in nature. We can find this number on our periodic table as your molar mass, which you've seen before in a lot of the calculations you've done. So, for example, for sulfur, the relative atomic mass is 32.06. The formula for relative atomic mass is the relative atomic mass is equal to the atomic mass of the first isotope times its relative abundance. Then you add it to the atomic mass of the second isotope times its relative abundance, and so on and so forth, depending on how many isotopes are naturally occurring for that element. Here's an example we'll do together. So silicon has 3 isotopes that are found in nature. Calculate the atomic mass of silicon based on the 3 isotopes and the relative abundance summarized in the table below. So we have silicon 28, silicon 29, and silicon 30. Silicon 28 has a 92.23% abundance and obviously an atomic mass of 28, which is what the name is giving us. Silicon 29 has a 4.680%, and silicon 30 has a 3.090%. So taking that information, we would get our relative mass formula, which I've just summarized as the molar mass of one isotope times its percent plus the molar mass of the other isotopes, so on, their percent. We sub in our data, and we obviously convert our percents to a decimal place, so you just divide them by 100. And doing that, it gives you the answer 28.09. And then our units are U, because this is in relative atomic mass. Here is a second example. So we have chlorine that has 2 naturally occurring isotopes, chlorine 35 and chlorine 37. And its relative atomic mass was found to be 35.35 U. What is the abundance of each isotope? So when you have a question like this, the first thing that you're going to do is we need to find 2 different percent abundances, and we're told that they only have 2 naturally occurring isotopes. So that means the first one, it could have been either, but for this example I picked chlorine 35, has I said their percent abundance is X. We know because it's a percent and that this number is like a decimal place out of 1. Then the chlorine 7's percent abundance is 1 minus X, because whatever chlorine 35 is, chlorine 37 is the rest of the thing, because there's only 2 naturally occurring ones. And then we have both of their atomic masses, individual atomic masses, from their names, chlorine 35 and chlorine 37. We know that's 35U, and we know that's 37U. Then we would, using the same formula we used before, we'd sub in all our missing variables. So our relative atomic mass is 35.35. We have our percent abundance, which is X, and 1 minus X for chlorine 35 and for chlorine 37. And then we have their masses, which are 35 and 37 respectively. Then it is just simple algebra. So we would expand out these 2 brackets, which would give us minus 37x and plus 37. We'd get it so that our x was only on one side. So it would give us minus 1.65 is equal to negative 2x. And then to find out x, we just divide by negative 2, which gives us x is equal to 0.825. Then that gives us the abundance of chlorine 35. To find chlorine 37, we just put put that back into the 1 minus x that we created before. So we have 1 minus 0.825 gives us 0.175. And then to convert those back into percents, you just multiply both by 100. And that gives chlorine 35 a 82.5% relative abundance, and chlorine 37 a 17.5 abundance. Those are the main types of questions you're going to see related to relative atomic mass. So either finding what their abundance is when you're given the relative atomic mass, or finding out what the relative atomic mass is when you are given their abundance. Adding more, isotopes just doesn't change what you do to solve the question. It just makes maybe the math longer. But with these examples, you should be able to do any question relating to relative atomic mass.